Good evening. My name is Masaki Gondo. I'm a CDO of the company called eSOL. We are a Tokyo-based company. We have about 400 people with about less than 400 engineers. And we're doing basically embedded system software. We provide a real-time operating system to our customers along with some engineering services. And so today, I don't know if it's coming up. Yep. I'd like to talk about our operating system is called eT-Kernel. I don't know if you have heard about what's called T-Engine or T-Kernel. If you're doing some of the IoT, Internet of Things kind of stuff, Dr. Sakamura of Tokyo University did the specification, and we took that specification and implemented it as a proprietary operating system and extend that feature. And that's what we call our product as a eT-Kernel. And we have a partner called SRA. It's a Japanese partner who has a long time experience of Qt platform, and they did a port to our operating system. So what we did is that include the Qt platform into our own SDK, and we provide that to our customers. So today I'd like to talk about my topic there is that Qt on eT-Kernel blending Qt with RTOS for future smart devices. That means some of the car infotainment system. Many of our customers are from automotive space, and they use our operating system. And those kind of systems are becoming very intelligent, more and more intelligent. And I like to define in a much broader sense what the smart device is in the beginning. And later talk about some of the blending technology options. That's blending between real-time processing and media-rich type of application. And what the pros and cons about those options are. And then I talk about Linux compatible multicore RTOS, which is exactly what our operating system is. And just to briefly touch on some of the internals of the things like inter-working of Qt and real-time application, and some tooling of the system analysis that we provide. So we have only, I have only 30 minutes or 35 minutes, so it will be a very quick run. But we have a booth there at the exhibition space. We have our FAE there, and we have also a demo of this SDK running Qt 4.7.1. So if you need more information, then please visit our booth and talk to him. OK? So very big space, and so you can have 3 chairs each, maybe. So take your time. All right. So what's smart? So this is my own sort of definition. So iPhone comes to many of you as what the smart device is, and it's sort of revolutionized what the smartphone is. And to me, what the iPhone is really, what it did really is integrating various sensors and also intuitive user interface. And the context information, the context is your surroundings, so the device surroundings of devices, and also network information blended together, along with that, the sensor-based information. So that's real-time information blended together with archived information, either it's archived locally on the disk or over the network. Some of the pictures that I have here on your left side or right-hand side, that's a pretty famous Japanese smartphone application called Sekai Camera. It's a world camera in the direct translation. It uses your smartphone's camera blended together with a network database, so it uses all the sensors to get the coordinates with the GPS and where it's directing to with the digital compass. And with the camera image, it's blending, gets meta information from over the network, and then blends those two information together and display it at the same time. So it's type of AR, augmented reality type of application. This is one example of blending real-time information along with the archived information, making it quite smart device, smart application. What you have on the other side is actually uses our operating system. Is one of the latest car infotainment system from Pioneer. It's called AR navigation system. So it does its blending. You see the camera here, the CG camera over there in the center. And it blends in that video image along with the map information. So, and displays that in real time while you drive. So it's actually going AR in real time. So these kind of things are really making things smart, blending smart real-time information along with the archive, either network-based or archive-based information, media information. Another aspect looking at, from the real-time perspective is that real-time brings quality to your smart devices. If you're developing some kind of music application on the smartphones, you may know, or even you can find as just a smartphone user, you could find a pretty good music instrument application on either iPad or iPhone. But you don't really find so much on so many such applications from on the Android. And I talked to one of those application developers, and they said it's quite difficult to do the same thing that they can do with iPad on the Android system because Android is too slow. And it lacks, well, it's not technically too slow. It's not real-time enough. So when you play those kind of instruments, when you touch the touch panel, you want the sound to come right back. And that's more, it has some real-time requirement to it. And it affects greatly your feeling, the playability of the application or the music instruments. And that's really real-time processing that's required there. And now we are talking about very, well, quite complex, but still simple application like that. But what I have on the other side, I have Yamaha's electronic piano. This is quite an expensive one. One of the state-of-the-art electric piano. And what it uses is not Android or iOS, but it uses real-time operating system to drive it. So this is for mostly like a professional use type of musical instruments, but it's all done electronically by software. So, and it uses real-time operating system underneath it. So not everyone wants a professional device on your smartphone, but the point I'm trying to get out of here is that the real-time capability of the system actually does add quite a lot of quality to the system itself or the smart devices. Also, there's other stuff you need to worry about when you're developing smart devices. The one thing is about the widening spectrum of device grades. What I mean by that is that nowadays, many your customer, if you're OEM, you have different spectrum of markets that you have to deal with. Maybe in China, you have a much cheaper grade system, where in Europe or Japan, you really want a very high-end type of systems. But time to the market is quite tight. So what you want to do is that you want to reuse as much resources as possible, not just hardware, but the especially software and also the technical expertise of the engineering resources that you have. So what you want to do is that you want to use the same platform over the different spectrum device grades in a sort of product line fashion. That's what I'm saying here. And also the second thing, other stuff, is that the safety and reliability, especially in the space in the automotive systems or the aerospace, which we also have a customer there in the aerospace, it's quite important that the safety and reliability is quite important. And that's another aspect that you have to think about when you are searching for the blending options that you might want to choose. And last but not least, the you have to also deal with the semiconductor trends. Now it's going multicore basically. the demo that we have in our booth is also multicore Cortex-A9 dual-core-based system. Our OS runs in SMP fashion in the platform, and many of our customers started using multicore systems. So you have to be also capable multicore system if you want to go to high-end. But still, you want to use the same software set with a single-core uniprocessor-based system too. So those are things you have to take care when you're doing smart devices. So you need intuitive user interface and networking, exactly what Qt provides. But you also need real-time reliability for intelligence and safety. And you also need to think about scalability for differentiating, but yet cost-effective product lines. So that's the challenge that I put here is a blending of both media-rich and real-time and reliable world in a scalable manner, and including multicore. So what are the blending technology options? So that's blending, once again, as I said, it's a blending of real-time and reliable processing with media-rich or network-based processing and blended together. That's possibly even on the multicore. I have 4 options here I have today. First one is Linux standalone. Second one is a sort of hybrid operating system architecture where you might have Linux and real-time operating system. The third one is a typical RTOS standalone. The last one is a Linux compatible multicore RTOS. So start with the Linux. Certainly, looking at the advantages of it, pros of it, Qt, Android, and all the major application platform runs on Linux. And it's also sort of open source standard. Everyone uses it, a large number of developers worldwide. So that's definitely an advantage. And of course, it's multicore ready. Looking at the sort of cons of it, it's not a real-time operating system to begin with. It's just not architected that way. It's architected to be a desktop operating system now, well, blending with server processing, but never towards really real-time processing. It's not good or bad, it's just not that way. So if you want to do real-time processing, Linux is really not the architecture that it fits. The second thing is a lack of scalability to the lower end of spectrum. That means the Linux kernel is, well, quite big compared to RTOS. With our operating system, you can come down to, even with POSIX systems, come down to somewhere between 300 to 500 kilobytes, where with Linux, you might have 4 megabytes. So it does affect how scalable you can go when you're doing product line type of system development. Second option is that the hybrid operating system approach where you have Linux, could be Windows, and RTOS. And we are seeing quite a few examples, actual system in last couple of years, even using the RTOS being an operating system, and especially with multicore coming into it. And the advantage of that is that, well, it's functionally distributed AMP. I don't know if you recognize what's AMP. It's asymmetric multiprocessing. So it's functionally distributed, separated. So real-time side is done by real-time operating system, and the media-rich side done by the Linux side or the Windows. And it's clean separation. So real-time OS for real-time processing. So it does what it can do. Same with the Linux. So that sounds pretty simple. But the cons of it, if you want to do smart devices, the intelligence comes from blending of real-time information and media-rich information blended together. So you have to integrate those two information. Now, that's where advantage of AMP type of processing becomes a disadvantage. AMP is, by architecture, it means to separate things. But when you want to integrate it, you don't want to separate, you want to integrate it. So inter-OS communication, for example, becomes quite difficult because it's two different operating systems, different architecture, different APIs. And so that could be bring a complex issue when you're doing intelligent processing. The second thing is that it does not work well on a single core. There's a technology, if you use a hypervisor or a virtual machine, it is possible to run 2 operating systems on a single processor, but it does add lots of overhead to it. So it has a limitation to it. So that's because you have 2 operating systems on a single processor. So that's a hybrid operating system. The third one is a typical RTOS standalone. Advantage of that is that, of course, it's RTOS, so real-time processing is pretty good. And it's reliable, because that's what the real-time operating system is used for. And it's much smaller kernel than Linux. But if it's just typical RTOS standalone, software reuse is often limited, APIs being proprietary, unless it supports sort of full-range POSIX APIs with process and layers and shared libraries and stuff. There's only so much you can reuse from the open source space, because many of them are based on the POSIX or Linux, vice versa, pretty much the same meaning. So you cannot reuse those things, including Qt to some extent. And it's often not scalable to higher end of the spectrum. It's just not architected with like things like memory protection, process model type of system. It's not possible. So it can be used with a smaller system, but not the larger systems. And the multimedia is not typically available. Multicore support is often limited. That's what the typical RTOS standalone is. So finally, the Linux-compatible multicore RTOS. It's Pros. It's RTOS based, so it's good with real-time processing. And it offers, it's Linux compatible, meaning it offers POSIX APIs, a full set of POSIX APIs. And then it's quite compatible to Linux application. And it's capable of multicore. And I will explain it later, example of our operating system, how we do the multicore processing. And it has seamless integration between real-time and media-rich application, because it's a single operating system offering real-time processing, and also can do multimedia stuff on top of Qt, for example. And also multicore is, of course, possible. Disadvantage, if you look at it, one thing could be a limited offerings. It's not all providing these kind of properties. These are sort of our competitors. eSOL is us. NEA and QNX offers a similar type of platform, but that's maybe OK. And also Green Hills, I think. But there's only a few players there, so you don't have much choices. So limited offerings. And it's just not as popular as Linux. So you might, it depends on customers, how you value that, but it's not as popular as Linux. So you might indicate some unknown risks. So this is an example of our own SDK. You can see underneath, on the bottom, it's BSP. It's board support package with the device drivers support. We have the kernel core, and we have POSIX subsystem on top. And on top of the POSIX layer, we have a whole Qt application framework ported onto our operating system. And you do have regular OpenGLES, OpenBG drivers, and network stacks, USB stacks, and storages. And we have our own dedicated IDEs that works with our operating system. And these are what we're showing at the booth there. So you might want to take a look at it. This is just a little bit going deep into how blending or the integration of media-side Qt application and real-time processing is made possible in our architecture. Our kernel, eT-Kernel, offers real-time APIs, which is based on the T-Kernel APIs by Ken Sakamura, TRON specification. And it's used for many years, more than 30 years in worldwide in real-time processing. And we also have, to allow the use of open space applications such as Qt, we offer full POSIX subsystem and the libraries. And those two runs on the same kernel. So T-Kernel real-time application can run in concurrently with POSIX applications such as Qt application. And we have a POSIX subsystem that allows the Qt to run. And we have a native TRON system that allows real-time application to run. And these two spaces can share things like device drivers, and also middlewares. It allows the use of those system-level software while the application can run independently. Because to the kernel, it's basically the task the same way. It's just that the POSIX thread has more properties than the real-time thread or real-time task. And the real-time task being much simpler than the POSIX thread. So it runs on the same kernel. This shows some of the different ways you can use to communicate between Qt application and real-time T-Kernel POSIX application. So Qt application runs as a regular POSIX process, and you could have a multi-threaded. And our operating system supports the shell library just like Linux does. So Qt is actually ported. Qt for embedded Linux is ported to our operating system, and you can use one way to communicate it. You can just use POSIX APIs, inter-process communication APIs that POSIX provides, either messaging or semaphore or whichever that you switch to use to communicate to real-time application. The other way you can do is that you can use actually called T-Kernel APIs from Qt application and just directly talk to the T-Kernel real-time application. Even the other way that you can do is that you can use some kind of pseudo device driver and communicate through that driver channel. So, or you can, the fourth choice you can have it, you can have your own communication middleware, or not communication middleware, or any middleware that you want to use to talk between those two applications, and you set the library APIs. So, and it's all on the same operating system, so it's quite easy. It's basically talking to a regular task to another task. So there's no complication between mixing, for example, two operating systems. It's a single operating system, so it's very seamless to talk to each other. Now I'm talking a little bit about the multicore support that we provide. We provide the same thing Linux provides, but since we are a real-time operating system, we do a little bit further. We definitely provide later SMP load balancing, scheduling, processing, and also the what with Linux called the CPU thread affinity. So you can bind some thread to a particular processor core. But in addition, what we offer what we call the single processor mode, which is sort of blending in AMP type of scheduling into a SMP system. To begin with, it is SMP operating system, but when you use that the single processor mode, SPM here, abbreviated, these tasks on the these blue cores here, C0, C1, this is a quad-core system example. These tasks 1, 2, 3 always run on C0. And on the C0, all the other tasks from C4, 5, 6, and task 12, these tasks will never run on C0. So when you're doing SMP load balancing, if the C0 becomes idle, then if you have ready thread or tasks on the other cores, and it will migrate to C0. but that will not happen with SPM. So that sounds like a sort of waste of CPU processing, but it's quite important to assure real-time processing, and that real-time is about being able to forecast when some particular processing starts and ends. That's what real-time is. So, and what you actually have, that is what you actually have in the AMP system. The thread will never migrate from one to the other. So this SPM scheduling mode assures real-time processing by binding threads to a core and only those threads to that core. So, and it can be mixed in with a regular SMP domain that you have on the C2 and C3. These are all done in a SMP load balancing fashion. And still, it's a SMP operating system, so the APIs between these cores are transparent. So you don't have to worry about using some special APIs to communicate to threads on the other cores. So that is what our multicore edition of the operating system are doing. And if you're into things like hypervisor, we have actually the partitioning technology on top of our operating system. I'm not going to go into the detail because it could be long. So, but simply put, it is possible to say if you have a multi-core system and you want to partition cores, say real-time processing on one core and other non-real-time processing on the other cores, but you don't want to interference between these two partitions, for example. Because your real-time processing is much more critical, whereas a multimedia application possibly can be rebooted if you got some error, but not the real-time application. And this memory partitioning that we offer allows a protection of the real-time processing from the non-real-time processing. And when you're doing the mixture of the real-time application and media-rich type of application, and of course, you have to do the optimization to your system. Then it becomes quite important. You have the ability to optimize, well, to profile what your system are doing, what your real-time threads are doing, and non-real-time threads are doing. And it could be more complicated if you have a multi-core system. And it could be really complicated if you have a dual operating system set up, because you have a different tooling for two operating systems, so you cannot combine those two information. So that's another advantage of using a single operating system. You have a single view of the system profile. Example here that I have is a snapshot from our tools. This is a sampling-based tooling called a real-time profiler. This is a snapshot of a quad-core system. And it shows what percentage of each processing core are used for each process, or the thread, or the functions. It's layered on that way. Modules, process, threads, and functions. And the picture you have on your right-hand side is that these are plotted over the time. So if you want to say examine your boot performance, say if you want your system to boot in, say, 30 seconds, but it's actually booting taking 2 minutes, what you can do is that, and you don't know really what's going on, you have lots of software that's running on it. You can get everyone together and analyze it. What you can do is that with this real-time profiler, do the sampling for those 2 minutes, and the 2 minutes can be as long as here. And you can see at glance approximately how much, what time segments, what kind of processing are running. Say you might find some device driver initialization taking too much time, or some middleware setup is taking too much time. So this is a sampling based, so it's not very precise, but it's precise, correct enough to get you the big picture. Then once you spot some particular software running not as you design, then you could shift to tooling like this. This is a trace-based, instrumentation-based tools. So it gets all the event trace information. So different from profiling tool. It's sampling based, it doesn't give you much overhead, but this is instrumentation based, but it adds much more overhead. But on the other side, you get much precise information. You already have what processing takes more time, so you don't really care how much the overhead is adding. You want to know what it's really doing. So this system trace tools comes into play to show the exact sequence what software is running where. And then you go on to, you could spot some system calls or some API calls that's triggering that sequence that you haven't designed, the way that's not behaving as you designed. So that's a quick run of operating system, what we can do. So the challenge was blending of both media-rich and real-time processing in a scalable manner, including multicore. And what we are doing is that using a real-time operating system, the Qt provides a media-rich side, and our operating system, the native real-time processing capability, there's a real-time side. And the scalability can be achieved by using a scalable RTOS, since our RTOS can be quite small. And especially with in today's morning discussion presentation of the Qt 5.0 roadmap, they are going a smaller memory footprint and much modular. So that makes it even much more desirable for a platform like ours, because it can be much smaller for lower end spectrum devices. And it's also capable of multicore. OK, so that's it. If you want more information about our operating system, these are some of the English-based technical articles. Mostly are coming from ARM's IQ magazine. ARM is one of our good partners. And also, we have some solution regarding Android. Android actually runs on our operating system, too, like Qt does. So you might want to take a look at it. OK, thank you. Any questions?
Hi.
Hi.
My question is related to your scheduling modes. Is it possible to run POSIX compatible code in the real-time mode, or is it only limited to your APIs?
You can run real-time POSIX application. It's here. I have a pointer. Say on the second line, eT-Kernel has a kernel space application layer in addition to process space. So of course, you can do process real-time application, but if you want to go the application to run much faster, you can actually call POSIX APIs from a kernel application. So it's just like an RTOS thread task, but actually you can call POSIX APIs.
Thank you.
Yeah. Anything more? That's it? OK, thank you.